Hello, welcome to another problem session. Today we have an interesting problem. It comes from JEE, Joint Entrance Examination in India. It's for advanced physics. It was a question in 2021. So if you have been actually practicing with me concept angular momentum for the last couple of weeks, this would be very easy for you. Because this is only actually the axis of rotation is fixed here, the direction is fixed, and so everything is really simple. So there is just one component of angular momentum vector. Okay, let's read the problem and see how I would try to do it. Maybe you can try to do it now and then come back and check my answer. Okay, so the way I read it is you have this a thin circular disk of mass m. So you have this rod, and then there's a disk here. Both have same mass, but probably there's a pin here, and the disk sits on that pin, and it's kind of rotates. So this is kind of I would call it a spin motion, and in this spin motion the angular velocity is 4 omega. So omega spin is 4 omega around this. So if this was the axis, if everything was kind of fixed, it would just rotate like that. But then this structure is fixed to the rod, and rod is rotating with angular velocity this omega. So the whole thing is rotating. So at some other time, the disk is over here. So if you call this a z-axis and call this an x-axis and call this y-axis, so this thing is kind of parallel to the xy plane. So for the spin, angular momentum of the spin is pointed up, and then there is a disk plus the rod as a rigid body is rotating about this, and so this is, you can say, L orbital for everything. So it's kind of the orbit is that. That's the orbit, and the radius of the orbit is 3/4 a. Okay, so angular momentum will be kind of sum of the angular momentum of all of these things, right? So the principle will be angular momentum is sum of all the angular momentum. So I is rod and the disk. So there are two bodies here, and we just have to add up angular momentum of the both of them. So let's look at one at a time. So angular momentum of the rod is easy to work out. So angular rod is axis is here for this, axis for the rod is here, and angular velocity is like this. And if you use right hand rule, is in the z direction. So the direction is z direction, and the amount will be about this axis, z axis, about the z axis, and it's omega like this. So if you look at just the rod, then that just equal to z hat, and I'm looking at from the edge, from the center. I is 1/12 m, and the length of the rod is a square plus the distance from here to the center of mass. This is the center of mass. So M, capital M, A over 2 square. So that using the parallel axis theorem is like this, or you may already know the answer. The whole thing is, this is 1/3. So that's z hat 1/3 m a square omega. So that's for the rod. And next we want to do L of the disk. So the disk is there's a spin and then there's orbital. So L of cm, that's the orbital part, and L about cm, and that's the spin part. So let me do the spin part. So the spin part is very it should be a right hand rule. Again, it's the parallel to z axis, so we have a z hat, and axis for the spin part is here. And so you can see from there the angular momentum is half m, and the radius of the disk is a over 4 square, and the angular velocity of spin is 4 omega. So that's for the spin part. How about the orbital part? Orbital part is I put all of the, for the orbital part, we imagine the entire mass is placed at the center of mass, and center of mass of the disk is 3/4 of a from here. And so this is going to be, again, we're using a right hand rule. Again, it is z hat, and it's going to be entire mass at this radius 3 over 4 a square. So that's the moment of inertia, and this one is going around with omega, not 4 omega. This one was going 4 omega, but this one is going omega. So I need to add these guys up. So you have a z hat, and you're gonna have m a square omega, and so it's some factor will come from here, 9 over 16 come from here, and this is going to be 1 of the 4 will cancel 1 of the 4, so it's going to be 1 over 8. So now I need to add these with that, and in the question you have this kind of form, and we're supposed to get an n. So I'll try to get the 48. Let me pause this and do this calculation and come back. Okay, so I went ahead and did this calculation, and because I'm going to go towards that answer, there's a 48 down there. I'll just go ahead and work out factor with 48 here, and then I just multiply by 48 down here. So this gives me 27, because 9 times 3 is 27, and this gives me 6 because of 8 times 6 is 48. And when I add this up, I get 33 over here, multiplying this whole thing. I do the same thing for the rod, and I make the 48 the same because of that, and then the factor that should be to make it 1/3 is 16. So when I add these up, so the answer will be z hat m a square omega over 48, and this 33 per 16 is 49. So the n equals to 49. That's the answer. Let's check. Okay, how about we extend this problem and suppose we ask for kinetic energy. What will be the kinetic energy, which is not asked in this problem, but might as well have been asked. So how would we do that? So the extension will be kinetic energy of everything, and I'll next do that. You can pause the button and you can try to do it yourself and see how far you go. Okay, I'll clean up the board so I can do the problem on a clean place. Okay, so let's do kinetic energy. This is the extension. We're extending to kinetic energy. Well, just like angular momentum, kinetic energy is also kinetic energy of pure rotation, like a spin motion, plus kinetic energy of cm. So that it's a spin or rotation, and rotation about cm and off cm is separate like that. So let's look at the same way. So kinetic energy of the rod is going to be 1/2 I about this axis, this axis. Okay, so axis A, which is the same as z axis. So axis A and omega square, and for the rod, and there's 1/3 ma square omega square. So this is just simply 1/6 ma square omega square. How about kinetic energy of the disk? So just like there, we have this and this separation, so that of the cm of this motion, that's going to be 1/2 I about this axis B, I about axis B, and 4 omega square. So this omega rotation is 4 omega square, plus half axis about this A, omega square. So this now this one is simply 1/2 ma/4 square. That's the radius. That's the radius of the disk. But this is of mass m located at cm. It's not for the whole disk. Is it as if the entire mass was placed at the center of mass? So this is, you might say, I of cm, and I of cm is m 3a/4 square. So now let me pause and kind of add this. Okay, so I hope I didn't make a mistake here. ma square omega square 25/32. So I need to add these two. So net kinetic energy will be just ma square omega square 1/6 plus 25 over 32. And let me add this up. So after some doing more calculation, you can see I have this as an answer. So the basic fact about both angular momentum and kinetic energy of rigid bodies is actually about cm plus L of cm. Kinetic energy is same as kinetic energy about cm plus kinetic energy of cm. And so this one is just m nvcm rcm across this. So you can just use a basic particle definition, and this one will be some kind of rotation, and so this you have to use I omega, you have to use a vector to get this vector out. Okay, I think that's sufficient for now. I have to see you another problem session. Bye.